I hope you enjoyed the lunch break. Food is a very important part of the TNG culture, so I hope we met the expectations here. We definitely bribed the weather got successful. So yeah, welcome. When looking around, nothing has changed software development so much in the recent time like LLMs did. And currently, when looking around, many of them are fully proprietarian with Anthropic, OpenAI, and others. So therefore, looking at the open weight and open foundation models is very important, and that's the reason why I would very welcome you and introduce you our today's speaker, Lucas Atkins. Lucas serves as CTO at RCs, where he spearheaded the development of the proprietary training stack of their open weight and open foundation models, but he is a real expert in AI, and reading through his CV is very impressive. He already developed text-to-speech systems with automotive giants like Volkswagen, Ford, BMW, and Hyundai, and was in there well before the current surge of AI. He also was in the development for a translation system in the Arabic context with the UAE. He partnered with AMD in 2023 and 2024 to develop how do you use GPUs for enterprise model training. And now he is responsible at RCs for making open weight and open foundation models, the training more efficient and pushing it to the limit, being currently the standard made in America for this open technology. Looking forward to your talk, training 400 million models of expert from scratch without losing your mind. Lucas, stage is yours.
Well, thank you very much for the introduction. I'm very grateful and happy to be here. Yes, my name's Lucas Atkins. I'm currently the CTO at RC. And a little bit about us before I dive into the context of the talk and how I'd like to frame it. We started in early 2023, shortly after the ChatGPT explosion. With Mark, our CEO, was early on at Hugging Face, and he knew from his time there and from my experience before that enterprises and small businesses, or just businesses of all types, were going to struggle adopting these systems at scale. They work quite well for POCs and small usage sizes, but the margins became quite difficult as you scaled up and as your usage hit, the capacity that you were able to spend on tokens, let's put it that way. Startups are typically more willing to be loss leaders and eat those margins to build up a user base to then try to, monetize those later. But enterprises that couldn't, we're going to have a difficult time. So for 2 years, till, roughly early 2025, we were primarily a customization company. If you were an enterprise, say, making an invoice processing app, and you had done your POC or your work with something like GPT-4, or at the time like 4 Turbo, and you were getting to production and you realized that the price you were paying for tokens was very difficult, or you were dealing with sensitive information that you couldn't send off to a closed API, we would help work with you to develop a hyper-specific small language model, typically based off of something like Llama, that was like uniquely good at that specific task and very little else, which had the benefit of being very fast, very cheap, and it would run in their own environment. What ended up happening was a lot of the, at least Western open source models, stopped being released. And that wasn't a particularly bad problem, though we knew it could be, though it wasn't really damaging until, funny enough, DeepSeek, not even V3, when their R1 model came out. A lot of the enterprises we were working with at the time suddenly became very aware and conscious and concerned about what base model you were starting from. Many of them would not allow us to use base models that came out of China. And that didn't sit right with us. If we were going to succeed, we wanted it to be because of something we did and work within our control. But if, the opposite's true, if we were going to fail, we also wanted it to be because It was within our control. We didn't want to be at the whims of some Western conglomerate deciding that they were no longer interested in releasing open models. So instead of just starting from pre-existing base models, we decided to try doing our own. We did a 4.5B that released late July of last year. And the excitement from our customers, from our investors, the general community, and the kind of AI space was it was palpable. And it gave us the confidence that we could probably go all the way. And so we kind of set ourselves a very ambitious goal of between end of July, so early August 2025, and January of 2026, we wanted to release a 400 billion parameter model. And easier said than done, right? You talk to a lot of people, and they, especially those who aren't super in the weeds, and they're like, well, you did a 4B. Why don't you just use 100 times as much compute and you're done? I mean, I guess on paper they're not wrong, but there's some nuance to that. And so the other kind of constraint we had there was we did not have unlimited funds. We had raised enough. I mean, at the time, we had about $30 million in our bank account. But we had raised kind of as a post-training, almost SaaS type business in kind of Western VC world. And a lot of these models that people release are quite a bit more than $30 million. So we had to figure out how to do it for very cheap, relatively. And that meant that we weren't going to spend more than 20, which, again, is a lot to me, but in the grand scape of, the grand scene of training LLMs, it's actually nothing. Now, add to that the fact that we had 30 million in our bank account when we started, and I'm trying to set the stage for some of the pressures that might have been on us. Now, one of the ways we went about doing this was kind of ruthlessly compartmentalizing what we could do and what was kind of out of scope for us. And the first thing we wanted to do was, okay, well, if we're going to do a 400B, it obviously should be an MoE, a sparse MoE, with mixtures of experts, and those, while they're more efficient to train, they're considerably more complex than your average dense transformer. And so we didn't jump straight to the 400B. We did a 6 billion parameter, 1 billion active model that we called Trinity Nano, and we also did a 26B, 3B active model that we called Trinity Mini. They were very good models, but they were very much to de-risk the run that I'm speaking on today. And those released early December. And the reason we released those early December was because on December 1st, we had 2,048 B300s coming online for 30 days only, meaning we had to do this entire 400B run in 30 days. And the reason we chose the shape we did, 400B with 13 billion active, not just 13, that'd be very cool, but probably not very good. The reason we chose that shape was because we kind of reverse engineered, okay, given we wanted to get through, at the time it was 20 trillion tokens, and we have 30 days, we have 2,000 GPUs, therefore we needed to have, I think we calculated it down to like 4,500 tokens per second per GPU every day for 30 days. And then I had them add an additional 500 because the synthetic math is always imperfect. And then we found that this shape worked quite well that enabled us to do that. And so when I came to speaking on this run and kind of this journey, and what I thought I could be uniquely beneficial, what my experience could be uniquely beneficial to attendees was not a walkthrough of the tech report. Now, we do have a tech report we're very proud of, and frankly goes into more detail than you're probably used to getting out of a tech report. But one of the reasons we wanted to be so open was because one of the ways we were able to train this model and do it at all was because of the lovely reports that had come out of labs prior, and then us kind of reverse engineering the things that they don't speak on, which is interesting. If you're looking at a tech report or a model card from a lab, obviously what's in the tech report is interesting, but what's always fun And often the more key thing to pay attention to are what are the things that they don't speak about, or the stuff they talk around or just mention briefly. It's like, oh, then we generated some data and trained on it. Okay. How? And that'll often tell you the thing that they find to be their most core IP and mode. But when I was thinking of this talk, it wasn't just go through the tech report, because you can read it. And frankly, the people who were the core writers of it can go into much more detail than I ever could. So I thought, what could I speak on that I think would be helpful? And I think it's kind of telling the story of the run through the eyes of someone who had a lot of pressure on him. The stakes could not have been higher. And as you'll see, almost everything that could have gone wrong went wrong. Yet, at the end of it, we had a 400 billion parameter model that, while being half the size of active parameters to its peers, is extremely competitive with not just the models coming out of China, but also our peers over at Anthropic on agentic, long horizon, long context tasks. So bear with me. I have one of my researchers here who was nice enough to come down from Berlin. He might have some PTSD from some of the things I speak on today. But I'll get through this, and then at the end, I believe we'll have 10, maybe 15 minutes for a Q&A, which I think oftentimes can help me frame things that are, to the specific audience that I have. So, as I went into, the 400B was a pretty big bet. If we were doing this properly, we might have waited a year and a half instead of 6 months, or less than 6 months, frankly, by the time we got going. We probably would have tried to raise more funding first, which is not fun and probably wouldn't have worked. We would have gotten a 2,000 B300 cluster for a year and done very large-scale ablations and ensured that when we went to train this model that it was going to be exactly how good we wanted it to be, and we didn't really get to do that. That wasn't really an option. Our motto has become constraints breed creativity. If we had infinite money, we probably would not have made as good of a model because we would have just been able to throw compute at it. Whereas this forced, our team to be quite nimble and creative with a lot of the engineering decisions we made. I did mention we did the 6B and the 26B. What is different about this was, as I said, those were mostly to de-risk the run. Just, can we do an MoE at all? Can we handle load balancing? Can we make a performant model? So the answer was yes, but when we were going into large, as I said, we had to kind of build the architecture around the compute that we had and the amount of time we had it for, which meant that we changed actually quite a bit between the smaller ones and this big one. We went twice as sparse, meaning when they refer to sparsity, we're talking about how many total parameters do we have, so 400B, versus how few active per token do we have, which is 13. The typical sparsity is for 128 experts total, you have 8 active every token. Had we done that for this model, it would have probably been 26 to 27B active. So we were about twice as sparse as any model had been before, at least publicly. 400B brings some pretty difficult, checkpoints are a lot bigger than a 26B, especially with the way we were doing it. Every checkpoint was about 1.5 terabytes. And we were having to, you're having to sync those across all of the different nodes. You're having to upload those to S3. And ideally, you have a local hard drive big enough to handle checkpointing regularly at scale. And then we were also doing a different optimizer sharding strategy than we did for Mini and Nano. The benefit of doing a small model is you can kind of get away with data parallelism, right? Where you have one copy of the model on each GPU, because it can fit in the VRAM, and then you just spread the data out across those, and it allows you to train a lot faster. It's not nearly as complex. When you go to this size, though, I mean, even if you have B300s with like 192 gigabytes of VRAM, each model was, as I said, about a terabyte in size. So you have to shard not just the data, but also the model across those GPUs, which introduces, additional complexity. So for the first 3 days, it kind of went as we expected. You get the cluster, and when I say we released the small ones early December, I mean we released those December 1st, and the cluster for this one started December 1st, which meant that we knew that, you know, when you get a cluster of this size and you're getting it set up, and we use Slurm for these, that there's typically going to be some growing pains when you first get on a new cluster, right? You have to get familiar with it. You have to, you know, stress test it, put it through its paces. And we expected that it would probably be 2 to 3 days before we were going in earnest. And that's largely what happened. Early on, we had some weird issues with, we were trying to do async checkpointing. So you're kind of checkpointing at a given step while you continue training, and you have part of the process and go towards saving the checkpoint so that you're not running into, you know, pausing for 15 minutes every 100 steps to save a checkpoint. There was weirdness where we would restart from an async checkpoint and the loss would be drastically different. We weren't having deterministic checkpointing, which is never good. So we switched back to synchronous checkpointing. There was some oddities with the way we were sharding muon. That was one of the things we did that was a little atypical at the time, was we bet big on a new optimizer called muon. Kimmy had done it, so we had some belief that we knew if implemented correctly, it worked. The problem was there weren't a lot of correct implementations online, so we had to, you know, we hoped that we had done it right. We hadn't, but it was an easy fix, and that took about 4 hours to fix. So by the 3rd or 4th day, we were training properly. We had the tokens per second that we'd calculated roughly in line with what we needed. Things were going well. Except for MaxVio. And MaxVio, it seems like violation, and the way we think of that is, given your 256 experts, how many of those are well balanced? Meaning, for every token, are you reasonably splitting, are each of the experts getting split amongst evenly? The reason you want that, well, it's you don't want it to be too balanced, but the reason you don't want it to be really unbalanced is, say you have 256, but only 100 ever get routed to, well, then you just have 156 dead experts. And, you know, those weights might as well not exist. It's a waste of compute. And you might as well not be training a model of that size. So you don't want that. You also don't want it to be too balanced, because then you're not encouraging the experts to gain any specificity or any you know, knowledge unique to them. Now, with MoE models, it can get a little tricky because it's not like you have one that's like a code expert and one that's an expert in speaking, you know, German versus one that's an expert in speaking English or Mandarin. They're token level experts, so it gets much more difficult to interpret that if you're viewing it from the brain of a human. But ideally, you want there to be some level of imbalance, but minor. And what was happening was MaxVio is basically a ratio of what is the difference in routing, tokens routed to from your most routed to versus your least routed to expert. And ideally, this is a metric, at least the way we calculated it, that would be under 1. So like 0.2, 0.3, that was what we considered healthy. Once we got to about 100 billion tokens, it started to really climb. And that was annoying because loss looked great, grad norm looked great. All of the things you would typically associate with a healthy run looked fine. But that made us very uncomfortable because the fear there was, okay, well, it looks fine now, but either when we get to 500 billion tokens or we get to 1 trillion or, you know, forbid 15 trillion tokens, then that starts to collapse. You have the loss start to explode, you have the grad norm start to explode, and then you can't recover. You kind of have to start over. So this was really nerve-wracking to us. Now, what was especially frustrating, as I said, you know, all of this looked fine, was that we had not had this problem with Mini and Nano. And we were using the exact same training pipeline. So the shape of the model was slightly different, but the techniques we used were the same. You know, we used the same kind of load balancer that DeepSeek did for V2 and V3. and those had been sufficient at that sparsity and at that scale. That was not the case here. And the reason this was especially scary was because this was not something that was an easy fix. There was no literature that kind of had talked about, people had talked about the difficulty in balancing experts, but it had never been, there was no smoking gun here as far as something we were missing that would account for this. So what ends up happening here is we made the decision not to continue until we'd solved this. Now, that's hard to do, because to put it in context, each day of training was about $275,000. So us delaying even one day was difficult, let alone what ended up being 5. But the reason we did that was, and this is what I said to the team all the time, was like, it doesn't necessarily have to be novel, it doesn't necessarily have to be a new model, it doesn't have to be super fancy, but it does have to be good. And us releasing a 400B model that wasn't competitive at all is a much worse look than not training one at all. So we wanted to be sure that we did this right. Now, one of the ways we did that was, at least in my head, I didn't share this with the team, but I kind of reverse engineered when our final day would be trying to fix it at 400B. Because the alternative was you go back to the same sparsity you had with Mini and Nano, because we highly suspected that this was as a result of having 256 experts and only 4 active. So if we'd gone back to 128, or even 256 and 8, we suspected that this would not be as much of a problem. So now, if we went back to the normal sparsity, but at the same size, the model would have taken twice as long to train, which would mean that we would, in our 30 days, only get through maybe 8 or 9 trillion tokens, which we didn't want to do. Or it meant that we could cut the model size in half and do a 200B 13B active, which I don't think any of us really wanted to do, but it was kind of our nuclear option, if you will. And so the way I dealt with this problem in particular was, okay, I'm going to reverse engineer how long it will take us to train that 200B. And then as soon as we hit the date where if we went further, we wouldn't be able to fully train it, that is when we would start, which meant we technically had until day 12. Now, we could have gone all the way to day 12. Luckily, we didn't end up having to. But had we gotten to day 11 and fixed it, and we could do the 400B, well, then we were only going to get through like 12 trillion tokens with the 400B. So there were a lot of compromises. There was no way we came out of this fully unscathed, but I think optically there were ways to do this properly. This was exacerbated by the fact that when we released the small ones on December 1st, we announced the size of large. I will never do that again. Because if we went and, because now, if we never announced the size and we went to 200B, it's not really a problem. We make it seem, like every tech report, we would just make it seem like that was the plan from the beginning. But when you say you're doing a 400B and then a month later you release a 200B, probably not the best optics either. So we were kind of, I'm glad we did announce it because it forced us to really fix this, but probably not a level of pressure I'll put on myself or my team ever again. So this is something that comes up a lot when I deal with most problems in life, but especially when it comes to research and when I have younger researchers or maybe those without a formal academic education. When it comes to debugging things, especially stuff with AI where it's hard to unit test expert balance. There's not like a test you can run that you can be sure that you're going to have it fixed. And there's often not clear, the metrics you see, like MaxVio, right? That is a reflection of a symptom. That is not the cause. It was a symptom of a greater issue. And so finding what that issue is to fix can often be quite tricky. In my philosophy, what I'll see with some of my younger researchers is, it could be a tokenizer. Let's put it this way. It could be a tokenizer. It could be, it could be the data we're throwing at the models way out of distribution. It could be that muon was still sharded incorrectly. It could be, obviously, the sparsity. There were a bunch of things that could have been the problem, and what they'll end up doing is doing small tests in each area, but never getting too deep, hoping that one of them will just be the problem and they can fix it. That'll work sometimes, but when you're dealing with a problem like this, where there's no really easy way to define it or find it or diagnose it, my philosophy has always been like lower the search space. Spend your initial debugging time finding what it isn't, so that once you've zeroed in on what it could be and what it likely is, you can get really deep. And so the first thing we did was like we tried with a different tokenizer. We tried with like the llama tokenizer, just to see if we got any different. It was the exact same, meaning, okay, it's probably not a tokenizer. We tried with Atom, your more traditional optimizer, to rule out muon. It was the exact same. We tried with a more like FineWeb, like a publicly available data set that many people had trained models on. Same problem, which meant it wasn't the tokenizer, it wasn't the optimizer, and it wasn't the data. So we kind of really felt at that point, okay, it is the sparsity and a result of doing this at scale. And so that allowed us to spend the rest of our time focused on how do we handle the load balancing and what are our experiments and ablations going to be to fix it. And this is a rule of thumb that I like to follow when it comes to debugging of all types, but especially AI research, because when there's $275,000 on the line every day, ideally you're doing experiments that are going to get you back running as soon as possible. We managed it. Oh, this was something that I said quite often. Maybe not with these exact words. I might be, Lucas Krauss, my researcher, might, say I said it quite differently. But my overall philosophy was like, if this goes well, if we're able to fix this, if we're able to train the model, if we're able to get to 400B and release a competitive model in the timeline that we set, right, 5-6 months, it's everyone's responsibility. Everyone is, that is on everyone. Everyone deserves the praise, everyone deserves the credit. I deserve very little. If it goes very bad, and we don't fix this, or we are only able to do a 200B, or we're able to do a 400B, but only for 7 trillion tokens, that's on me. And one of the reasons this was important to me is I didn't want people making really brash decisions or instinctual decisions because they were afraid of like their job, or they were afraid of it reflecting poorly on them. So they would kind of YOLO something, and it might not be the best use of their time or our compute. And so this is a very important philosophy just in general as a manager and as a leader, but I think that especially in times of like extreme crisis, they're very important. And it's important to tell people, because you might be able to give that impression with your behavior or personality, but a lot of people need to hear it, especially when they're so locked in on staring at a weights and bias graph. The other thing that I like to do, and this again comes from life, and this is something that I believe very strongly in, but is especially when it comes to debugging, is like, what should we be focused on at all? The things we can change, not what is out of our control. So taking inventory of what are the things we can actually do in a blatant fix versus what is entirely out of our control, right? Obviously, we had a lot of investors that were interested in this going well, We had spent and reorganized our entire 20-person company around doing this for the last 5 months. So obviously there's a lot of sunk cost in there. If it doesn't go well, maybe we led people astray. The overall, AI industry is rather ruthless with criticism. You very rarely hear good job, but you'll certainly hear if you did a bad job. Whether we as a company made it out of this. And then, blaming everyone. Like, there's all these things that we could focus on and could think about and could use our attention on, but ultimately we can't change any of that. Or if we could, it was because we did this well. And so what did we have to focus on to do it well? We could focus on doing proper ablations. We could focus on ablating things at a smaller scale but the same sparsity. We could make a new load balancing approach and try that. We could focus on who was making these decisions, and we could focus on what the next test is. There's that, it's like a very stoic phrase of what is in the way becomes the way. And I like to focus on that a lot when it comes to these kind of problems of like, the only thing we're worried about is what the next problem is. And in this case, it was what's the next test to run. Another thing we did, which I had in a slide here, but when I first made this, I had like 24 slides, and I was like, oh, that means I'm gonna have to do like 1:30 per slide, and I didn't want to do that. So one of the other things we did was we kind of made like a little bit of a decision tree, which was planning out what we were gonna do if our ablations if like one ablation didn't work. So we were gonna do this experiment, ideally that fixed it, but if it didn't, what was the next one we were gonna run? And it was always like, if we got good signal from one experiment, we were gonna go in this direction. If we got no signal or no change from an experiment, we were gonna go in a different one. And that made it easy because we had people across, the entire world. We had people in Europe, we had people in India, we had people in Korea, we had people in America. And people were kind of working around the clock, which was lovely, but we don't want people waiting 4 or 5 hours while I'm sleeping to do the next thing. So if they get a result, they can parse it, look at the tree, and go on to the next thing. However, early on, we did have some people restart an ablation in the middle of a run while we were asleep. And it was just because they had kind of panicked about something and convinced someone to restart the run, which meant we wasted $100,000 because the run was going fine. And so this was actually quite important, as we set like a group of 4 people who all needed to agree on something if we were restarting on the big cluster. Now we had smaller bits of compute that people were running their like smaller scale ablations on, which you could do whatever you want with. That's what they were there. But with the 2000 cluster, obviously that's the one we're doing our larger ablations at, where we're getting more data and trying to actually see if we're fixing it. And so we kind of made a tree of who was deciding. It was me, it was our head of pre-training, and then 2 of the gentlemen that were focused on infrastructure. Ideally all 4 were agreeing on something, but since all of us were in San Francisco, we did, as long as 3 of the 4 were around, we would make that call. So that was something we set up very early, and you can't blame that person. It's a very scary experience to just know that everything like this is on the line, and if it doesn't go well, there could be stark consequences. Not for them, not like no one was going to lose their job over this because but if the company went under, well, they'd lose their job. So the people were stressed. So what we ended up doing is kind of what I mentioned. It was like we had our conservative track, which was on like the really big cluster where people were throwing in, the ablations that were one at a time, but a little more minor, because we were trying to get a lot of information, and that also meant we were adding quite a lot of logging. Like one of the weird things is like the more logging you add, the slower training will take when you get to this size. So especially when you have a specific metric for every MoE layer, for every MoE expert for every layer, I think we had 75,000 like unique metrics for every expert being sent. And so those were obviously being done on the bigger cluster because it could handle that kind of load, and we were able to get that amount of information and parse through it. Then we had our more ambitious track, which is where, again, we had people with smaller compute, whether it was multiple nodes or just a single node, and they were running their more ambitious, throw anything against the wall, see if it works. And then once someone would have something promising with some results that looked good, we would add those to the conservative track and try it at a larger scale. What ended up happening over the course of, this probably took 5 days. It was, I think, the end of the 4th day when we ran into this problem, or at least we noticed that this was going to be a problem. And then it was about 5 days of not knowing if this was going to work and throwing everything at it and hoping it would. So we ended up doing a few things. We were using some of the experts and some of the attention layers we were doing at MXFP8, which we switched back to doing BF16 for everything. The downside there is you train a little bit slower. Your model's a little bit more large natively, but when you're doing something like this for the first time, I always stress lower the number of variables. Like I say, lower the search space, lower the number of variables. How many things could go wrong? And we know that you can train a model at BF16 quite well, so we went back to that. We added a Z-loss, which was a known technique that was quite good, but it helped the logits that the router was using to route from growing into from getting far too large. We added like a sequence-wise auxiliary loss, which came Quen. The Quen team did that quite well. And one of the things we did when we first ran into this issue is we tried to find other models, whether they'd been released recently or previously, that were at a similar sparsity. And the closest was like the Quen 3 Next model, which at the time was 80B 3B active. We ended up being a little bit sparser, but they were very close. So they unfortunately didn't go into a ton of detail about their load balancing, but we were able to take at least sequence-wise auxiliary loss. It was something that in our ablations, it didn't hurt. So whether or not it was the fix, we don't know, because we threw 6 things in at once. But it certainly didn't hurt. We also added a few more dense layers. So one of the things you'll do with an MoE of this size is you'll typically have 1 or 2 or 3, like out of your 60 layers, in our case, you'll have like 1, 2, or 3 that are dense. And that is too early on is to help with stability, because instead of every single token or every single sequence going to a brand new expert and the router not being able to understand who to go to for what, you have at least 3 layers that are always getting routed to. And we upped that to 6. So that's one of the reasons also the model was originally 420B 13B active. One of the concessions we actually made was bringing it down to 400. Now that was fine for us. Our investors didn't love that because they wanted to call it the largest open model ever trained in the United States, which meant that we had to beat 405B. But I thought that they would probably be happier if we had a good model than if we had a really bad one at 420B. So we went to 400. And then this came later. We didn't do this. This wasn't an immediate fix, but we introduced there was quite a lot we found that we could improve with the data loader specifically. It's like how we were chunking, how data was being passed to the model, and how we were ensuring that as much of the chunks being sent to each GPU and each sequence were actual, like, fruitful information instead of just padding tokens. Because one of the things you'll typically do is, if your sequence length was 4,000, ours was 8,000, and you have one document that is 6,000 tokens, instead of trying to find another document that has like 2,000 and then adding that, which is ideal, a lot of data loaders will just add padding tokens, like a token that you put at the end just to pad it to 8,000, so you're still training at 8,000, but it's literally just called pad token. And so we added some more sophisticated work to ensure that we could do the first one, right? We could take 6,000 and add 2,000 from another one. Well, the good news is that fixed it. I didn't even get into like the most important one. Wait. SMEBU. This was something we came up with ourselves, which we were actually extremely proud of. It was basically, so when you're doing load balancing, what you're basically doing is if one expert is not getting routed to more than another, at least within the range you're happy with, you'll use like a bias to correct it. You'll basically, the next time the router goes, you're going to force the router to see that one as more valuable than it did last time. And what we felt was happening was that we were overcorrecting, meaning like, because one expert would be super unbalanced because you have 256, you would be applying that same bias that you were for the big one to a model, to an expert that wasn't nearly as unbiased, and that was causing it to then become super routed to, which was having this kind of domino effect across all of our experts. We were pretty sure that was what was happening after we'd done all of our tests. So we developed, there were a lot of things we could have called it, but what we ended up doing was adding like a momentum-aware algorithm to our load balancer. So we would adjust it, each expert, based on how out of balance it was, discretely. So if there was one that was super unbalanced, that would get a higher bias, versus if there was one that was only slightly unbalanced, that would receive a very small update. And we firmly believe that this was exactly what fixed our run. We're very proud of it because it wasn't in any publication before. It was something we came up with ourselves. And then 3, we're fairly certain that we could go significantly sparser using this technique. Like, again, we're 256 with 4. We could probably go. I would bet we could probably go to 1,000 experts with only 8 or 4 active and still be just fine. So, yeah, this is taken directly from our weights and biases from our run. Like, that was it before. It was going all the way up to a pretty extreme level of unbiased or of violation by the time we let it go to like 200, 300 billion tokens, whereas it was incredibly smooth after that. We didn't run into that issue. We did restart. We didn't start from 100 billion tokens, but it was only 100 billion. We were trying to do, we also lowered our total number of tokens. As I said, again, we were doing 20 trillion. And so what we did was we do it in phases. Like phase one was 13 trillion tokens of like really high quality web text data. Phase two, you'd add a lot more math, science, code, and a little bit of instruct data. And then in phase three was like our fewest, it was 3 trillion, but it was your highest quality tokens that you'd been able to curate. And so what we did was we just lowered the amount we did in phase one. We did 10 instead of 13, and then that way we could get through all of our phase two and our phase three. And the reason I wanted to show it this way was it did not, there were many worlds in which it did not end up going well. And it's one of the things I'm most proud of about this was, yes, I'm proud that we moved so fast. I'm proud that we were able to reorient our company in this direction, and that 13, 14 researchers who had never pre-trained a model in May were able to train a 400B that was competitive at the frontier by January. I'm obviously very proud of all that. But I'm proud of how we did it, and it kind of goes back to my thesis for how to stay competitive in this industry as it moves so fast now, which is pick things you have no business trying to do, and then bang your head against the wall until you do them. Because the resources are available now. The models are quite good. You're able to get a lot of domain-specific information that you used to not be able to. The resources are available, and the open source world is quite strong. As I said, the model itself, after we did post-training, ended up being very competitive. The reason I had pulled up our tech report, beyond to show you what the loss looked like at the end, which is like beautiful. And as you see here, this is when we did different phases, right? So here was we actually increased the batch size to get through more tokens. And then this is when we went into phase two. And then the last ones we went into phase three. And the reason I bring this up is just to show you the base model benchmarks, because this is something we were especially proud of. So it's probably not going to be very easy to see. It might be better. Oh, it's actually not too bad. So we're in green. And then Llama 4 Maverick, which was, we compared against, because one, it was like the last model of that size released in the United States. It's an open weight model. It was also a very similar level of sparsity. And then gray was GLM 4.5, which at the time was like kind of A, closest in size, but B, probably one of the best base models that had been released. And we were beating both of them on many, many benchmarks, and if we weren't beating them, we were extremely competitive, while having half the parameters, right? We were 13, whereas GLM was, I think, 34. And then the other thing, let me see, here. This was throughput. Because we were so low and we did some fancy stuff with our attention, we were significantly faster than DeepSeek and GLM in inference, which allows us to, we currently serve this model for 80 cents per million tokens out, compared to GLM and others where they're in the $3 range. And one of the reasons we're able to do this is we are so sparse. We handle long context and attention really well, but we're able to serve at a very, very, very quickly and serve a lot of users, which is very nice. And it ended up working out the way we needed it to. We're going to be able to keep doing this for quite a long time now. So we look forward to doing Trinity 2 here in the next couple months. Is it time for a Q&A? Yes, thank you.
Thank you, Lucas, for your amazing talk. I'm very sure there are questions. I thought that.
So thank you very much, Lucas, and congratulations. We would have loved to do what you did, but we didn't. What my impression is that you were able to really, really prioritize the different work parts that had to be done, and you made decisions like, okay, data comes from datology, full stop. Or let's ask prime intellect for these. So essentially you were able, like an orchestrator, to say where the best musicians come from, where the efficient musicians come from. But how did you optimize this like overall delivery network because you were under such resource constraints?
It was easier than you'd think, simply because when you give someone the option to train a 400B model, they're typically pretty interested in doing it. So I didn't have to, there wasn't a lot of, having to, push people as much to do things, or there wasn't as much orchestrating. It was also in the best interest of everyone involved. That's part of kind of that ruthless compartmentalization I talked about, where if we were going to do this in such a short amount of time, how could we focus on the things that we thought we could be uniquely good at, which we felt was architecture and the training pipeline and the MFU and getting it to train fast. A lot of that, phase 1 web text work we outsourced to Datology, which was very helpful, which allowed us to focus on like our highest quality mid-training tokens. And then Prime Intellect was very beneficial in helping us manage a 2,000 GPU cluster for the first time. I don't know. I mean, I think with any of these things, it's with anything in life, but especially when it comes to this, like you pick something very ambitious, and then you can like reverse engineer how to do it. If we wanted to have this model done in 6 months, and we knew how big we wanted it to be, so what are all the things we have to do in between in order to get it done? And you can keep subdividing tasks into smaller tasks as they get larger in scale, and can be scary to think about when it's one big, to do. And then I'm very proud of my team. I mean, everyone wanted to be there. Everyone wanted to be involved, and it couldn't have been done with another group of people. So.
Further question, I think there's one in the back.
Thank you so much for the talk. I was wondering, do you plan to go even more sparse with your next model? So is this the direction you want to go? And what pros you expect from going more sparse?
The answer is eventually. Our current plan is to, as I said, the smaller ones we've done before were half as sparse. I think for our next slate of models, we're going to do smaller ones that are in the same sparsity as large. Meaning like if we did a 20B, it'd be 500 million active. That might be what we're doing. But the reason we're doing that is because then you can actually do proper scaling ablations. Like we can actually, what you do is something called like token per parameter ratio scaling, where, okay, given a level of compute for a fixed model size and architecture, the more compute we throw at it, whether that's by increasing the parameters or the amount of tokens, how good does it get at each of those scales? Which if we do that across 4 model sizes, right, ranging from 20B all the way up to like 400, it allows us to very accurately predict how good a model will be if we go even further, which means we can know, say we want our next big model to be the best open weight model in the world, it will allow us to very accurately predict how big it has to be and how many tokens we have to throw at it in order to do that. But there's reason to believe that many of the closed models are unbelievably sparse. I mean, if you're talking like Mythos is like 10 trillion, maybe 100B active. I mean, those things are very, very sparse. So certainly, as we get more mature and we do more of this, I bet we're going to get pretty sparse too.
Further questions? Probably in the back.
Fantastic talk. Thank you so much.
Thank you.
When you had the slide for the conservative track and the optimistic track, and you said that some teams would throw something at the small nodes, if the issue is scaling, how can you detect if what they're proposing is helpful or not if the issues don't emerge until you're training on the big cluster?
Yeah, that's what's annoying is you can't. But what was helpful here is we did, you try to, with any kind of debugging, you try to recreate the issue. And so what they would do then is they would make a very, very, very sparse small model. So like 500 million total, 2 active, right? Like they would make it very sparse and then recreate the same conditions we were seeing and then apply load balancing strategies. Like that's what SMEBU eventually came out of. We were able to have a super sparse small model, way sparser than what we'd done, and it maintained a good expert balance. So that was what gave us confidence. So instead of scaling the parameters, we scaled the sparsity. But to your point, that's one of the downsides of having to work off smaller compute is you can't ever really be sure.
One last question.
So hello thanks for the good talk. And I was curious about the training data. You said for the training methods you got inspiration from like the open models. Did you have something, let's say, unique in how you chose the training data, or was it like an open corpus or something?
No, so yeah, when we got into this, like that was one of the things. I was like, if we only trained on data that was publicly available via like FineWeb or something, we'd probably only be as good as other models trained on those. So we have a partner company called Datology who kind of specializes in large-scale pre-training data, and we worked with them quite a lot throughout this whole experience. And we did quite a lot of work ourselves too, but ultimately it was synthetic data. So of the 17 trillion or 20 trillion that we were ready to train on, 10 of that was fully synthetic. That does not mean like taking instruct data or reasoning data and training on that, though we're certainly going to do that in the future. What this meant was taking like a 10-page Wikipedia article and condensing it down into one page. So you're trying to make the tokens more dense, as well as like rephrasing information. So, and then you would show the model both. So the model would see the original seed data, which may have been like a forum page, and then you would rewrite it to say the same thing, but with different language. Well, we would do multilingual. We did quite a bit of that, but like different verbiage. And the reason you would do that is you teach the model to interpolate between two different ways of saying the same thing instead of it learning to memorize the token. And I think that was one of our biggest, by far one of the things that was most beneficial to us being able to do this well. And that was kind of my marching orders to all the team, was like, get out of the data's way. Like, let's not be so adventurous and new that we're not going to let the data do its work. So, yeah.
With that, the time is over. Lucas is still around, so if you have questions, just pass by. And let's thank our speaker again.
Thank you very much.